Um, Hello, everyone. Welcome to the 109th meeting of New Directions in Group Theory and Triangulated Categories. Today, our speaker is Kabeer Manali Rahul, who is a PhD student affiliated with the Australian National University, and he'll be talking to us about metric, G-approximability, and some Brown representability theorems.
All right. Thanks a lot, Rudrudeep, for this opportunity to speak here. And thanks a lot for everybody who is here. So I'll be talking about some Brown representability type theorems. And the main sort of technical machinery which is used to prove these results is that of G-approximable triangulated categories, which in turn rely on this notion of a metric on a category. So let me begin there. So this notion is relatively old, the notion of a metric on a category. It goes back to Lauvere in the 70s. Okay, so the notion is as follows. Let C be a category. A metric is an assignment of a non-negative real number to each morphism, which satisfies certain properties. So firstly, we have that delta on the identity is 0 for all objects. And secondly, we have the triangle inequality, which is pretty much as you would expect. It's this for all composable morphisms. And yeah, so this is the notion of a metric on a category. It's sort of the way to think about this is that it assigns a notion of length to each morphism. But in this talk, we'll be more interested in metrics on triangulated categories, not all of them, but certain special ones, which brings us to this definition of a extended good metric. So let T be a triangulated category. An extended good metric on T is a sequence of strictly full subcategories, Mn, graded over the integers, which satisfy these three conditions. And I should say perhaps how one is meant to think about these. These full subcategories Mn somehow represent balls of radius 2 to the power minus n around the zero object. So let me first state the definition and make this a bit more precise. So the three conditions that these satisfy are that 0 belongs to each of these full subcategories, which if you think about the analogy makes total sense that these are balls around 0, so they should definitely contain 0. The second is that these are closed under extensions. So star here just denotes extensions. This sort of basically says that the metric is non-Archimedean, which is a condition we want to impose in this talk, though that is not necessary in general. And the third condition is that these balls decrease, which again, by the analogy, they should. So not only Mn plus 1, but its shifts, its suspension and desuspension is contained inside Mn. So how does one go from here to the definition of metric in the sense of Lauvere? The assignment is as follows. So given this metric M, we can define a metric in the sense of Lauvere delta M as follows. So firstly, we impose that sort of translation invariance, so to say, that the length of morphism F is defined to be the same as the length of the unique map from 0 to the cone of F, so which is this condition. And the second condition is that the length of a map from 0 to an object F is the inf of sort of the ball of radius 2 to the power minus n in which it is contained, which sort of makes the analogy precise. So this is the technical definition of an extended good metric for people who have seen the notion of a good metric defined by Neeman before. So Neeman was the one who came up with the notion of a good metric. And the only difference between that definition and this is that we are taking these categories over the integers instead of indexed over the integers instead of indexed over the natural numbers. So it's not a serious difference. So here are some sort of important examples of extended good metrics. So let T be a triangulated category, and suppose T has a T structure. Then you can sort of take Mn, the ball of radius 1/2 to the power n, to be the nth suspension of the aisle of the T structure. This defines an extended good metric. Analogously, if you have a weight structure or a co-T structure, then you can take the nth desuspension of the aisle to be the extended good metric. Of course, you may as well take the co-aisles and their shifts. That would also define an extended good metric, but somehow in today's talk, these will be sort of the important players. Do let me know if there are any questions at any
Kabir,
point.
when
Yeah.
you're writing your weight structures, the bigger than equal to zero, the smaller than equal to zero, you are still writing them as superscripts.
Yes. So all of the notation is cohomological, and sort of the co-aisle is the right orthogonal to the aisle in both the cases, and the aisle is written first and the co-aisle is written second. Is that fine?
Yeah, I mean it's sure.
Yeah. Okay. All right. Yeah. So with this, I sort of want to move on to the definition of G-approximability. But before I get into the formal definition, I'd like to sort of give an analytic analogy, just to sort of motivate motivate this notion. So the analogy is with Fourier series on the circle. And the circle I'm denoting by this. So the analogy is with Fourier series on the circle. So the category on the left that we'd want to consider are the integrable functions on the circle, complex valued. And the category on the right is the compactly generated triangulated category T. On the left-hand side, we have a metric which is given by the L2 norm. And note again that not all objects have finite length here, because the category that we are considering is the L1 of the circle, and the metric that we are giving is the L2. So it's a sort of an extended metric. And similarly, on the right-hand side, we it's part of the datum of the G-approximable triangulated category that there is an orthogonal metric on the category. I've not defined what an orthogonal metric is yet, but the point is that it is in particular an extended good metric. So that is all one needs to think about at the moment. And I'll come back to the definition of an orthogonal metric in a bit. Thirdly, there is a distinguished set of object on the left-hand side, which is given by these functions e to the power I and x, which satisfy this very nice condition that the orthogonal, on the left-hand side here, by the orthogonal, I mean the orthogonal in the sense of the inner product. If the orthogonal is 0, then the function must be 0. So the orthogonal in some sense is the orthogonal of all of these functions is 0. On the right-hand side, we have what I call a generating sequence. Again, the definition is pending. I'll come to it in a bit. But these are in particular a set of compact objects such that their orthogonal is 0. In particular, this forms the union forms a generating set, forms a compactly generating set. And finally, perhaps what is the heart of the matter is this approximating condition. On the left-hand side, we have that if a function has finite L2 norm, then for any integer that exists an object En such that the distance between En and f is as small as we want, and we can build En in a controlled amount of steps from the special set of objects in step 3. And this is essentially this theorem is essentially equivalent to the convergence of Fourier series in the L2 norm. And on the right-hand side, we have that if there is an object which has finite distance from 0, or equivalently, it belongs to one of the Rn's, then there exists a map En to f such that its distance is as small as we want, and the object En is built from the generating sequence in finite amount of steps. Again, I've not defined what this means, but for now, it means that it can be built from this generating sequence in n steps, capital N steps. I'll make this precise in a bit. So this is sort of the idea of G approximability, or sort of the analytic analogy. Now I'd want to even so still before defining G approximability in its full generality, I'd like to sort of look at two important cases which will be most interested today. The first is the notion of a approximable triangulated category. This was defined by Neeman. It's as follows. So let T be a compactly generated triangulated category with a compact generator G. Then we say that T is approximable if there exists a T structure and a positive integer satisfying the following conditions. First, we have that the nth suspension of G lies in the aisle of the T structure. Secondly, we have this Hom vanishing condition, sort of going the wrong way around when you think about the T structure in some sense. And finally, the condition which is sort of the heart of the matter, again, which is the approximating condition. If something lies in the aisle of the T structure, then there exists a triangle with D lying in the shift of the aisle and E built from the compact generator in n steps. And here I should make precise what this category is. This is the closure of G under coproducts. By coproducts, I mean all small coproducts, and allowing at most n suspensions, desuspensions, and extensions. So at most n suspensions, desuspensions, and extensions are allowed. All coproducts are allowed, and all summands are allowed. All summands. So this is the notion of an approximable triangulated category defined by Neeman. So a question which might arise to people who have seen approximable triangulated categories before is, why is there a notion of defining a more general idea? Like, why does this not cover everything which is of importance? And for that, so the answer is essentially that there are naturally occurring triangulated categories which cannot be approximable, but do satisfy a structure which is analogous to approximability. So here is just a sort of naturally occurring example. Consider a Noetherian scheme, and we consider this category, the homotopy category of injectives. So natural category is the incompletion of this category, of the boundary derived category of coherent sheaves. In particular, the compacts of this category are exactly, I mean, sort of are triangulated equivalent to the boundary derived category of coherent sheaves. Assume that T has a compact generator, which is required for the definition of approximability. This happens if X is J2, for example. Then condition 2, this condition cannot be satisfied unless X is regular. So in sort of very, very, very special cases. So this sort of shows that if one wants to study the homotopy category of injectives with similar techniques, one needs to modify the definition. And in this case, there is an easier fix, sort of easily stated fix, which brings us to this definition of a co-approximable triangulated category. The definition is very analogous. Let T be a compactly generated triangulated category with a compact generator G. Then we say T is co-approximable if there exists a weight structure or a co-T structure instead of a T structure. And an integer and a positive integer satisfying analogous conditions. The first is that the D-suspension of G now lies in the aisle of the co-T structure, the weight structure. There is a Hom vanishing condition. And finally, if there is an object which lies in the aisle of the co-T structure, then there is a triangle with E again being in the same thing, same subcategory generated from G as we talked about before, and D being in the D-suspension of the aisle this time. And we'll see that the homotopy category of injectives, albeit under special conditions, does satisfy this. Not always, but under some special conditions, it does satisfy this. For those who have seen Neeman's other work, might be familiar with this notion of a weakly approximable triangulated category. There is also a notion of a weakly co-approximable triangulated category. Again, sort of replacing everything else is the same. We just replace this category by this one, which is we just lose the condition on the number of lose the bound on the number of extensions allowed. So arbitrary extensions are allowed, closed under coproducts, suspensions, desuspensions, and summands. I forgot to write that. Whatever. Yeah. It's closed under summands also. All right. Maybe I'll, yeah. So now that I've given these definitions, I should state a few examples. So most of my examples in today's talk would be coming from algebraic geometry. So here are the examples. Okay. So let X be a quasi-compact separated scheme. Then this example is due to Neeman. The derived category of quasi-coherent sheaves is approximable. So this is an example. Yeah, so this is a highly non-trivial result, requires quite a bit of work. But basically, it turns out that for almost all reasonable schemes, the derived category of quasi-coherent sheaves is approximable. There is a sort of non-commutative analog to this. This is in joint work with Timothy Dedane and Pat Lang. So let A be a quasi-coherent sheaf of quasi-coherent OX algebra, then this category is also approximable. So, yeah. So these examples show that there are a bunch of examples of approximable triangulated categories. There are more examples coming from homotopy theory, etc., but I'll not get into that. So now we come to the example of co-approximable triangulated categories.
Kabeer, can I ask a very tedious question?
Yeah, sure.
Can you just go up a little bit?
Yeah, absolutely.
Amnon,
yeah.
Example number one.
Yeah.
So Amnon proves that DQCX is approximable, I know, but here you're writing that DQCX is the same as, like, putting the, like, looking at quasi-coherent cohomology and looking at quasi-coherent sheaves is the same thing.
Yeah.
For this triangle equivalence, I mean, this is fine with just QC plus S, or?
Separated is fine. Separated is
I
fine.
thought we
Yeah.
needed Noetherian or we locally Noetherian.
I
So
don't think that is required. I think this follows from
then
yeah, I
this,
mean, at least in the affine case, for example, this goes back to Bockstedt-Neeman, section 6.
right?
But in the non-affine case, I think one reference would be Lippmann's book on
Okay.
representability.
I mean, I
I
can say why
think
I
it's
was
uh-huh.
thinking what I was thinking,
Mhm.
because in the stacks project from, and that is one place where I
Mhm.
gone to on past
Mhm.
occasions for these kinds of
Mhm.
triangular equivalences. I think
Mhm.
they were doing it for Noetherian schemes.
Yeah, but there are experts here. Maybe, I mean, I don't know if
Anyway,
somebody
yeah,
can. Yeah,
that
yeah.
doesn't
I
matter.
don't.
Sorry,
Maybe I'm
sorry.
wrong, but
No,
no,
sorry.
no, that's totally fine. Um, yeah. In any case, he does it for the derived category of sheaves with quasi-coherent cohomology. So this part is definitely true. Uh, I feel that this should be fine, but if not, yeah, my bad. Um, yeah. So for examples of co-approximable triangulated categories, it's not quite as large a class, but let X be a quasi-excellent separated finite dimensional scheme, then the homotopy category of injectives, which some other people might recognize better as the int coherent sheaves, is co-approximable. Again, there is a mild non-commutative analog further. If A is an Azumaya algebra over X, Azumaya algebra over X, then K-ing of A is also co-approximable. For those who haven't seen quasi-excellence, all finite type schemes over a field are quasi-excellent. So every variety is quasi-excellent. But yeah, the definition is a bit involved, and I don't want to get into it at the moment. Anyway, so these are the examples of approximable and co-approximable triangulated categories. Okay, so I'll move on to to sort of trying to state the definition of G-approximability after this. So I'd like to pause if there are any questions at the moment.
Sorry, another tedious
Yeah,
thing.
no
So
problems. Yeah.
basically, when X is J2 and regular, you
Uh-huh.
have this category to be both co-approximable and approximable, right?
Mm, regular is enough. Regular is enough.
Yeah.
Regular is enough. Yeah, regular is enough. Because yeah, regular is enough. Although quasi-excellent does not imply regular, but yeah.
Mm-hmm.
Sorry, regular does not imply quasi-excellent, but it's still regular is also enough for this theorem. I just didn't state it because there the homotopy category of injectives agrees with the derived category of quasi-coherent sheaves. So
Mm-hmm.
sort of becomes
Okay, thank you.
less interesting. Yeah. Okay. So okay, then I'll move on to talking about the ingredients required for uh, stating the definition of a G-approximable triangulated category. First, an orthogonal metric. So let T be a triangulated category. We say an extended good metric is an orthogonal metric if the left orthogonal to its right orthogonal is Rn itself. And here, whenever I'm saying orthogonal, I mean orthogonal in the sense of homorthogonal. So let me just perhaps write this down. If A is a full subcategory of T, or A is just a set of objects of T, then A orthogonal is just T such that hom A comma T is equal to 0 for all A belonging to A. Yeah. And similarly for the left orthogonal, which I'm not going to state, but yeah. So examples of orthogonal metrics, both the metrics that I talked about earlier are orthogonal. Just comes from properties of T structures and co-T structures / weight structures. Of course, this won't change if you sort of replaced aisles instead of co-aisles. But we are still interested in the aisle metric for a reason. We'll come to that in a bit. Now let's come to the second part of this second ingredient which is required for stating the definition of G-approximability, which is the notion of a generating sequence. So let T be a compactly generated triangulated category. A generating sequence is a sequence of full subcategories of the compact objects satisfying the following two conditions. The first is that they sort of generate the compacts, and I'll make precise what these notions mean in a second. So this is the closure under finite coproducts and extensions and all extensions, and this is the closure under summarts. So the smallest category, which is closed under finite coproducts, extensions, and summands, which contains all of these subcategories, is exactly the category of compacts. And the second condition is a bit more technical. It says that Gn and its suspension and desuspension, they are contained in the subcategory generated under the same operations by Gn and its successor and predecessor, Gn plus 1, and Gn minus 1. The second condition is a bit of a technical condition. I agree, if that is what people are thinking. But okay. So before I get into that, we say that a generating sequence is a finite generating sequence if each of these full subcategories are finitely many objects. We note that the second condition gives us an extended good metric on the category of compacts, defined this way. You sort of take everything, all the objects below a certain point, and you take the category generated by that under summands, finite coproducts, and extensions. Yeah. Okay, so I should give examples of a generating sequence to make this sort of more concrete. So let T be a compactly generated triangulated category, and suppose it has a single compact generator. Then there are two sort of concrete finite generating sequences we can define on them. They're not just generating sequence, but finite ones. I mean, trivially so, as you'll see in a bit. You can define this and this, these two finite generating sequences on T. It's sort of very easy to see that these are indeed generating sequences. Yes. So even before I get into the definition of a G-approximable triangulated category, let me sort of already say how the notions of approximability and co-approximability that we have mentioned are subsumed by that definition. So let T be a triangulated category with a single compact generator G, then T is G-approximable with generating sequence 1, generating sequence 1 being this one, if and only if T is approximable. And I guess you can expect, you can already guess what the other one is. T is G-approximable with generating sequence 2, if and only if generating sequence 2 being this sequence, if and only if T is co-approximable. All right. So yeah, so somehow these two generating sequences are quite special, and they give back these familiar notions, or sort of maybe not familiar, but uh, sort of relatively easier to understand notions. Here is something about, yeah, maybe I should say this quite quickly. So given a generating sequence, we can define an orthogonal metric on T, which is defined as follows. Is defined to be the uh, left orthogonal to the right orthogonal of Gi, where I is less than or equal to n. Again, you don't need to sort of think too hard about the definition. The point is that in the two cases that we are interested in, or that we have talked about the most, uh, we get, for the case one, we get the compactly generated T structure generated by G. This is as in the work of Alonso Jeremias and Soto. And in the second case, we get the compactly generated weight structure, co-T structure, uh, generated by G. So this is as in the work of Bondarco and Poxtello. Okay, so we get sort of natural metrics, or sort of natural objects using these things. Okay, so this allows us to define the notion of a preferred equivalence class of orthogonal metrics on T, which might be interesting to people who have seen some of Neeman's work, because he defines the notion of a preferred equivalence class of a T structure, and there are analogous notions for those who are interested in this. I'll not dwell too much on this for now, just for the sake of time. So we can move on now to the formal definition of a G-approximable triangulated category. Again, do stop me if there are any questions at any point. Yeah, okay. So here is the definition of a G-approximable triangulated category. Let T be a compactly generated triangulated category with a generating sequence G. At the moment, we are not assuming that the generating sequence is finite. Then we say that T is G-approximable if there exists an orthogonal metric on it, and there exists a positive integer n, such that the following four conditions are satisfied. Again, the first condition is sort of technical. I've written it down already. It's sort of, you feel free to ignore it. Sort of pops up at a technical juncture of the proof, but otherwise it's not really very important. The other three conditions should be very familiar, sort of very similar to the analogous to the definition of approximability and co-approximability. So here is the condition one. This is contained in Ri for all j greater than or equal to n, and for all I in Z. So this is analogous to the first condition of the suspension of approximability and co-approximability. You might remember the first condition of approximability is about the shift of the generator being contained in the aisle, and the first condition of co-approximability being that the shift of the generator lies in the coil. So this is essentially the same condition, sort of analogous to it. Secondly, we have a Hom vanishing condition. We have Hom Gn Ri, sorry, is equal to 0. So this Hom vanishes for all n plus I greater than or equal to n. Again, something very analogous to both the definition of approximability and co-approximability. And finally, for the important approximating condition definition, which is as follows. For all I in Z and F in Ri, there exists a triangle uh, with, as you would expect, with D being in a smaller ball of smaller radius around 0, and E being built finitely from the generating sequence. Here I should mention what this thing is. This is the same, this is to expand it out, this is um, this category. And I'll explain what these terms mean in a bit. Just a second. Okay. So this is what this subcategory is. So this is again closure under summands, and this is closure under again coproducts. Again, here I mean all coproducts, all small coproducts, extensions. Sorry, and at most n extensions, and at most capital N extensions. So this is the definition of a G-approximable triangulated category. And now in the rest of the talk, I'll try to justify why this does give us something interesting. Oh, perhaps before that, you can analogously define a weakly G-approximable triangulated category by replacing the previous subcategory by this one. And here there is no bound on the number of extensions. So that's the only difference. I should mention here in passing that there exists sort of uses of weak G-approximability too. There are results on constructing semi-orthogonal decompositions. This is sort of analogous to, or sort of, there are similarities with work of Bondarko, and Kuznetsov-Schinder, and Sunanjang.
Can I ask a
Yeah.
this is
Yeah.
okay. So for your definition of G-approximable triangular categories, you are still requiring big T to be compactly generated, right? Is there
Yes.
any scope of making this work for well-generated triangular categories?
Depends on what you want to do with it. For representability theorems, the current proof seems delicate enough that it seems unlikely. But for some other results, maybe, because yeah.
The reason I ask is because, as you know, there are lots of
Yeah.
stack examples where DQC is
Yeah.
well generated but not
Yeah.
compactly generated.
Yeah. At the moment, even where stacks, like there is a single compact generator, approximability is not known. And yeah. So I think with stacks, there are even simpler questions which need to be tackled first, I think, before getting into something more complicated. But yeah.
Okay, thank you.
No problems. Okay. Um, yeah, okay. So yeah, with this reminder, let us sort of with this remark, I'd like to now talk about representability theorems. And today I'm going to be speaking about representability theorems in a sort of more general form than usually done. Again, this is not due to this ideas of thinking about representability in this sense is not due to me. Okay, so this is the general setup that I'll be thinking about. So let T be a R linear triangulated category for a commutative ring R. And let S be a full subcategory, a full triangulated subcategory actually, should triangulated subcategory. And consider the restricted unit of functor given by objects of T on sort of basically restrict the unit of functor onto S. Then we will say that a cohomological functor, by a cohomological functor, I just mean it takes triangles to long exact sequences. So we say cohomological functors from S to the category of R modules. This just denotes the category of R modules. We say a cohomological functor is representable if it is isomorphic to the restricted unit of functor on some object of T. here I should also note um, that that this restricted unit of functor need not be either full or faithful. So, okay, first of all, representability theorems. By representability theorems, I mean conditions on S, T, and H, which force H to be representable in this sense. Um, in this sense. And I'm also interested in results on Y being full or faithful, because that is also not a guarantee given that we're taking objects outside the category S. Otherwise, the unit lemma sort of covers that. Before I get into quote unquote new results, I should talk a bit about existing results, but I mean, of course, there is no sort of scope of talking about all the results in the literature. There are far too many. People have done a lot of work on representability theorems, and I'll just sort of talk about two landmark results, which sort of shaped uh, the area quite a bit. The first is the result by Neeman in 96, which says that so the situation is that S is equal to T and is compactly generated, and H preserves products. Then H is representable. This is yeah. This sort of follows the same argument as Brown's original result in homotopy theory. And the second is when S is equal to T again, and the category is strongly generated and is X finite over a Noetherian ring R. And the functor H is a finite cohomological functor. By a finite cohomological functor, I mean a cohomological functor such that this, oh, yeah, okay. Yeah, I seem to have made this mistake everywhere. It should be this. This is a finitely generated R module for all F in T. So in particular, what this implies is that what this is equivalent to is that H of sigma F is finitely generated for all I and is zero for I mod I larger than zero. In this case, also this functor is representable. This is a result by Vondal Vandenberg over a field, I think, and then improved upon by Rouquier over Noetherian ring R. So this is sort of, these are two important results in the literature, in the older literature. But of course, there are a ton of other results which I cannot get into. Okay, so with all of this said, let us get into the new results. Um, so here is the first theorem. So let X be again a quasi-accident scheme which is proper over a Noetherian finite dimensional ring R. Let Y denote the restricted unit of functor from the so from the derived category, bounded below derived category of coherent sheaves on X to functors on to cohomological functors on the bounded derived category of coherent sheaves. Uh, then the first result is that this functor Y is full, which is again, as I mentioned before, is not automatic, and full on D plus O of X, and then the essential image is all cohomological functors such that cohomological functors H such that H of F is finitely generated for all F. H of F is finitely generated and uh, this is 0 for large enough shifts for all f. So this, I mean, so any functor which satisfies this condition is representable by an object in D plus co of x. So in that sense, this is, I mean, yeah, so that is why this is a representability theorem. Secondly, so this was sort of the first part of this result. The second part of this result is that Y induces an equivalence of categories between um, okay, the intersection of the boundary derived category of coherent sheaves with so basically complexes of coherent sheaves which have finite injective dimension, this category, and finite cohomological functors on dB co x, which again, to remind you, are all the functors h such that this is finitely generated. So this is the main theorem for cohomological functors on the bounded derived category of coherent sheaves. Yeah. Okay. So there is an analogous result which is proven earlier by Neeman for cohomological functors on the category of perfect complexes. And sort of yeah. So what it says is that if you look at the restricted unit of functor sort of restricted to the bounded above complexes of coherent sheaves and sort of yeah, then again this functor is full and the essential image is these such cohomological functors. And again, Y induces an equivalence of categories between the boundary derived category of coherent sheaves and finite cohomological functors. So there is so we have also sort of identified, or Neeman has also identified exactly what the finite cohomological functors on perfects are. All right. Okay. Any questions at this point?
Is your new ground representability result the shadow of a deeper categorical result that you are not choosing to
No,
tell?
no, I'm going to get into that.
Okay, okay, sorry.
Though I might be squeezing things a bit because of time, but I'll try to that is what I'm going to try to state now. Because I sort of talked about the whole machinery of G-approximability, and I'll state it in that generality in a second. Okay, so if there are no other questions, let me quickly talk about the closure of compact objects. So let T be a compactly generated triangulated category with a metric. As the metric gives a notion of a length and distance, therefore it also allows us to define the notion of closure of subcategories. In particular, we'd be interested in the closure of compact objects, and that is defined to be the following. Following category, which let me quickly explain what this boils down to. These are objects f such that for each integer there exists a triangle such with E being compact and D in Rn. So basically, so this implies sort of that the cone of the morphism from E to F is sort of small because it lies in this is sort of the ball of radius 1/2 to the power n. And as this is true for all n, it sort of is zero distance away from the category of compacts, and therefore it is what you would, as you sort of, the natural notion, if you draw analogy from point set topology of the closure. Okay, and another subcategory that we'll be interested in, which is this, the bounded objects inside the closure of compacts, which is defined to be just the closure of compacts intersected with the orthogonal to the metric, which I define to be the union of the orthogonals. So I don't have time to dwell on these too much. Let me just quickly go to examples so that sort of at least in the usual cases, one knows what one is dealing with. Okay, so if we work with the Noetherian scheme and we look at the derived category of sheaves with quasi-coherent cohomology, and we take this metric, the one coming from the IL of the T structure, the standard T structure, we know that the compacts are the category of perfect complexes. The closure of the compact happens to be the bounded above complexes of sheaves with with coherent cohomology. And in the non-Noetherian case, these will turn out to be the category of pseudo-coherent complexes, but let me not get into that. The orthogonal to the metric is just D plus, just bounded below complexes, and TBC is just the bounded derived category of coherent sheaves, or bounded category of sheaves with coherent cohomology. So all of these are sort of well-known subcategories. In the case of homotopy category of injectives and the metric coming from the IL of the Coty structure, the weight structure, the compacts, as we know, is the bounded derived category of coherent sheaves. The closure of compacts is bounded below complexes of sheaves with coherent cohomology. The orthogonal to the metric is just bounded above complexes, and the intersection is just sheaves with coherent cohomology which have finite injective dimension. Here is there are a couple of homotopy theorists here. So here is an example from homotopy theory, which I'm not very comfortable with, but whatever. So if T is the stable homotopy category of spectra, then the compacts are the finite spectra. The closure of compacts is connective spectra with each stable homotopy group finitely generated. And TBC is exactly, the bounded objects are exactly the ones with finite Poznikov towers. All right, with that sort of lightning exposition into the closure of compacts, we can now finally state this representability theorem in its full generality, or the generality that I can prove it in at the moment, which is the following. So let T be a G-approximable triangulated category, and here a G is assumed to be a finite generating sequence, importantly, which is R linear for a Noetherian ring R. Further, we assume that the category is proper in the sense that the compact objects are finitely generated over R, the Hom sets of compact objects, that is. And we denote the restricted unit of functor Y by over the closure of TC. Then Y is full, and the essential image is exactly the G semi-finite cohomological functors. I've not defined it yet. I'll define it in a second, but you can imagine what it is. And Y induces an equivalence of categories between the bounded objects and all G finite cohomological functors on TC. Finally, I can end with this definition, just sort of funny, ending on a definition. So let T be a R linear triangulated category over a Noetherian commutative ring R with a generated sequence G. We say a cohomological functor with cohomological functor on T, or maybe I should say TC, Okay. This should be TC. With each h of f being finitely generated for all f, is G semi-finite if it vanishes on Gn for large enough n, and it is G finite if it vanishes on Gn for mod n large enough. Yeah, I think that's all I wanted to say.
Thank you very much. Can we all unmute ourselves and give Kabeer a round of applause now? If you have any questions for the speaker, please go ahead.
Sorry, so a standard question, whether these results are published. In particular, the part you say that you can produce semi-orthogonal decompositions.
No, neither these results nor the ones about semi-orthogonal decompositions are published yet. Both of these are part of my PhD thesis, and I'm currently sort of close to submitting my thesis. So hopefully, once that is done, in a couple of months, I'll try to sort of get the preprints out.
Thank you. Another question. So there is a recent work of Sosnima. I think it's not published either. He has made a talk, maybe not one talk, so about C categories.
Yeah.
And he related them to approximations.
Yeah.
Are you aware of this work? Maybe.
No, I just attended that talk also, but I've not thought about it yet. But there should be some connection with especially with co-approximability. There might be some, yeah. But I should write to him. I've not thought about it yet.
Okay, thank you very much. It was
Thanks a
very
lot. Thank you. Thank you.
Thank you, Mikhail. Any other questions? Do you get any interesting failures of ground representability through your methods? Because as you know, there was a like Kasakuberta Neeman, they had an example of a T that was both TR5 and TR5 star, with T and T of both failing ground representability. I mean, there have been other failures recorded. Do you
Yeah.
have any? I mean, is there any way in which you can see
I
where,
don't.
like, one of the conditions failing in your general statement could
Yeah.
lead to a failure of ground representability? That would
I
be very
don't.
interesting.
I don't think so. I don't think so. But yeah, again, I'm not. I don't know. The people who would know more about this, but I don't see something very obvious. Yeah, sort of. Yeah.
And what's the use of G semi-finiteness? You
What
ended
is
with
the use of?
definition.
Yeah, no. So I mean, the point is that it's always interesting when you can sort of represent some of these. When can you represent them by still small sort of objects of the triangulated category? So I guess that is sort of an interesting thing, that these functors, these cohomological functors, can be still represented by objects built in sort of from the compact objects in a nice sense. You don't have to resort to the whole categories. Still, the closure of the compacts. So I think, yeah. Otherwise, yeah.
Okay. Any questions, comments? Anybody? And I mean, obviously, I mean, this is a comment basically. So your TBC obviously recovers the Neeman TBC.
Yes. Yes.
So do you plan on sticking to just TBC for your writing?
I mean, I don't know. I mean, essentially, it's the compact. Sorry, it's the bounded objects on the closure of compacts. Maybe some other notation.
You should put a
yeah.
KMR watermark.
Yeah.
Right.
Yeah.
Okay. Okay, if we don't have any more questions, let's thank Kabeer once again. We have Alexander Perry from the University of Michigan next week, but the talk next week will be on Friday, not on Thursday, because a friend of mine is getting married on Thursday. And when I told him I couldn't come for the seminar, he was not too pleased. So anyway, hope to see you there. And Kabeer, can you hang around for a couple of minutes. And can you please send
Sure.
me the notes afterwards?
Yeah, will do.
Thank you all for coming. Bye bye.